So let us see some preparation methods of aldehydes and ketones or carbonyl compounds. Really speaking, this carbonyl compounds happens to be in the almost in the center of the chapter. So therefore, there are huge number of methods are there. So instead of taking 1, 2, 3, 4 up to 20 or 25 methods here, let us have commonize some methods into simple methods and special methods and so on like that. So in the first method, let us see simple methods. Simple means the method will be the easy and also popular also. In intermediate level books also the methods are mentioned. So therefore, let us call these methods are simple methods, right? So in the simple methods we have 4 different methods are there. The first one is the oxidation of alcohols. So 1 degree alcohol if I take like RCH2OH is a 1 degree alcohol. Careful oxidation of this 1 degree alcohol. If you use a strong oxidizing agent like dichromate and acid, it will become carboxylic acid. So careful oxidation means copper at 300 degrees centigrade. In fact, there are huge number of selective oxidations like openoid oxidation and so on, but let us use simple method, means simple reagents like copper 300 can take away the hydrogen from here and hydrogen from here, and the copper will be the catalyzing this dehydrogenation. It is a minus of H2. Really you find hydrogen is expelled out. So removal of hydrogen is oxidation. Adding oxygen is also oxidation. In this case, we are removing the 2 hydrogens and the compound will become into an aldehyde function is formed. So 1 degree alcohols, you get the aldehydes. So this you can have a standard statement. Like similarly, you can have a 2 degree alcohol. That means alcohol containing carbon has 2 alkyl. Here 1 alkyl, that's why 1 degree. 2 alkyls is 2 degree, 3 alkyl is 3 degree. So this is a 2 degree, or you can call it as a secondary, commonized secondary alcohol. Similar reaction will remove the 1 hydrogen from here, another hydrogen from there. The hydrogen gas is expelled. Copper is working as a catalyst here. So the compound turns into the ketone. So all 2 degree alcohols will give the ketone. Okay, right. Then you can extend the method, however it fails because 3 alcohols, if you have 3 alkyl groups like this, if you heat it, there is no hydrogen at here, so that H2 cannot be removed. Instead what happens, the whole OH and 1 hydrogen from the next carbon is removed as a water, and the double bond comes, the compound will become into an alkene formation. So this is differing totally, the reaction alkene is formed. However, we are not interested in this reaction because we are now not seeing the alkene preparation or tertiary alcohols property. So let us concentrate on this point. 1 degree alcohols on oxidation with specifically copper 300 will give the aldehydes, and 2 degree alcohols will give the ketones. The 3 degree, let us not go into that chemistry. 3 degree, however, is not going to give the carbonyl compound, but it is giving the alkene. I said this is an oxidation, it is, but contradictorily, this tertiary is becoming a reduction. Alcohol is converted into alkene, means it is a reduction. Same copper 300 on tertiary acting as a reducing agent in fact, but these 2 are oxidized to their next chapter. See, alcohol next chapter is aldehyde. So alcohol to aldehyde or a ketone means it is a promotion of the chapter. So oxidation. Going the chapters ahead means it's an oxidation. So it is an oxidation, but here the alkene next chapter is coming, so it is a reduction in fact. Same metal is acting as a reducing agent. But concentrate on these 2 points. 1 degree alcohol gives an aldehyde. So I can have a standard statement that I have an alcohol that on oxidation with copper 300 gives an aldehyde, means that is 1 degree. Or vice versa, I can say I have a carbonyl compound which can be prepared from that 2 degree alcohol. What is that carbonyl means? It is a ketone. So it is a standard fixed statement you can notice. Let's go for the second method. This is a hydration of alkynes. hydration of alkynes. So, alkynes means a triple bond containing compounds, we call it as an alkyne. So, simple first example, let us take the acetylene. Acetylene adding water, in fact the only water and acetylene has no reaction, but in presence of a few drops of concentrated sulfuric acid and some amount of mercuric sulfate, these two are catalysts. Actual reagent is water, H and OH is added following the electrophilic addition concept. So, what you will get is a vinyl alcohol is formed, but however this is a enol. So, enols undergo tautomerization. So, the hydrogen and the double bond will exchange, immediately you will get a enaldehyde is formed. Okay, right. So, this enol is specially called vinyl alcohol. So, vinyl alcohol becomes into the acetaldehyde. A similar case you can extend the reaction to the alkynes. So, it is propyne. A propyne under the reaction, it follows a Markovnikov rule. So, the OH minus adds in the center carbon. So, what you will get is a 2-propanol. This compound on tautomerization will give the acetone. So, if you observe one particular common fact here, ethyne gives a ethanol, aldehyde is coming. Propyne, we expect propane, aldehyde comes actually, we expect in fact. But what is happening is the OH here both are identical, either side it is terminal OH, but here the OH goes to the middle carbon obeying this Markovnikov rule, H plus goes to here, so that more stable carbocation comes on which OH attacks. So, OH coming into the center. So, carbonyl compound also becomes into acute. However, the minor product aldehyde may be formed, but according to this Markovnikov rule, the major product will be the acetone formation, right. So, this is also a simple method, in all intermediate textbooks it is well discussed. The third method, hydrolysis of 1,1 or gem dihalides. 1,1 or gem dihalides. Gem dihalides means both halogens will have on the same carbon, one carbon holding the two halogens. In fact, we have another type, if two halogens are side by side like this, they are called vicinal or vis dihalides. They are called gem dihalides or geminal dihalides. So, we need a 1,1 dihalo, because the concept is here very clear. If one halogen is there, do some base and hydrolyze it, one halogen will become into one OH, that is alcohols will be formed. If two halogens side by side are there, if you hydrolyze, you will get a glycol. Two halogens will give two OHs side by side, it is called glycol. But if two halogens on the same carbon, like for example, if you have a 1,1 dichloroethane. So, subsequently, if you hydrolyze with the NaOH aqueous solution, boil for some time. So, you get actually the answer is 1,1 dihydroxy or 1,1 diol is formed. So, in which that is lone pair or this bond electrons will come and one OH will go out. You can show the mechanism like this. So, electrons will come, or the lone pair you can use initially. So, HOH will go, the compound will become into the aldehyde formation. So, if 1,1 dihalo compounds are taken, you will get this type. If the halogens are there in between also, the position with reference to the second halogen and first halogen, if they should be on the same carbon, like this for example. If two halogens are here, you will get propanaldehyde. If the two halogens are on the middle halogen, then hydrolysis will give the 2,2-dihydroxy, which also undergo elimination of water immediately. 1,1 diols are unstable. So, therefore, you will get the carbonyl compound without any effort. Automatically, it will be given a carbonyl compound. So, if terminal carbon is having two halogens, you will get aldehyde. If the middle halogen is having the 2 halogens, you will get the ketone, and so on. So, if 3 halogens are there by chance, 3 OHs will come, and 3 OHs eliminate water, you will get a carboxylic acid. So, that comes under the acid preparation in fact. If 4 halogens are there, 4 sides, you will get 4 OHs, eliminate 2 water, and you will get carbon dioxide, that is CCl4, and total hydrolysis will give the carbon dioxide. So, like this, a concept is very clear that here, if 1 halogen is there in a compound, hydrolyzes to give the alcohol, 2 halogens side by side glycols, 2 halogens on the same carbon, you will get aldehyde or ketone depending upon the position. If 3 halogens on the same carbon, like this for example, if 3 halogens are there, 3 halogens will replace with 3 OHs, like this, 3 OHs will come. Out of that 3 OHs, 2 will eliminate as a water, you have no other OH to eliminate there. So, 1 OH cannot. So, moreover, the compound formed as now will have a COOH, this has got a very good resonance, therefore, the another OH will not eliminate, instead they get stabilized and the carboxylic acids are formed. So, if 4 Cls are there, I said carbon dioxide will come. That is wonderful concept. We have a very good number of questions on that particular hydrolysis of halogen compounds. What happens? So, we want a carbonyl for which 1,1 or 2,2 that is Visin geminal type of dihalides are useful to convert into this type of method. Let us see the fourth method. In this method, the pyrolysis of calcium salts of carboxylic acids. That means if you have a carboxylic acid, let us have a calcium salt. Calcium is +2, but this anion is -1. So, we will have a 2. You too can write such a compound as like this, RCOO minus, separate the bonding also we are representing here, calcium +2. So, there will be an ionic bonding between the calcium and the carboxylate anion of the COO minus. This compound is a solid. Most of the calcium salts or potassium salts, they are solids starting from the formic acid. So, this calcium acetate or calcium propanoate, whatever the acid you take, it will be solid. Take the solid, go on, heat it. Don't add any reagent or not even catalyst also. Just heating, and pyro means temperature, nolysis means breakdown. So, by applying the temperature, if you can break down a organic compound into pieces, you have this type of the description, pyrolysis. Pyrolysis means merry heating. So, just by heating, if you go, and I think this a box mechanism may be shown, a calcium carbonate is formed, the RCOR turns up into a ketone. So, whatever the calcium salt you take, it converts the corresponding ketone, and this side RCO, this side R is becoming into a ketone, and the calcium carbonate however will not be evaporating, but the ketone comes out as a vapor, and that you collect, and just like a distillation, the ketones will come out in the flask, from the flask as a vapor, because carbonyl compounds will have a less boiling points when compared with the calcium carbonates. So, therefore, any calcium salt you take, corresponding ketone is formed, but you can have a commonized phenomena. Let us have a carboxylic acid containing n number of carbons, 5 carbons or 6 carbons. So, in this n, you have taken a 1 more. So, therefore, n number of carbons you have taken twice, isn't it? That from the total carbons, 1 carbon is lost. So, if let us take, if a 3 carbon acid I have selected, 3 carbon acid means twice you have taken, 3 plus 3, 6. From that 6, 1 carbon is lost. So, you will get the 5 carbon, that is 2n minus 1 carbon containing ketone, you will get 2n minus 1 carbon containing number of the carbons will be there in the final answer. So, the n number of carbons twice you have taken, from that 1 carbon is lost as a calcium carbonate. So, 2n minus 1 number of carbons will be there in the ketone. So, if I take 3 carbon acid, 3 plus 3, 6, right. then that 6 minus 1. So, therefore, you will get a 5 carbon ketone. That too, another observation is the keto group in the center. 5 carbon center means on the third carbon the ketone will be the symmetric ketone. So, 2 R's will be identical. By seeing the 2 identical carbons, one should get an idea that this symmetrical ketone must be formed from a pyrolysis of a calcium, isn't it? Calcium salt of the acid. So, this is one observation. If the instead of the this is let us take one. Another observation is instead of the acid, bigger acid, let us take only the small acid like formic acid. The formic acid calcium salt, if I take, what happens? Calcium salt, formic acid will lose this calcium acetate, that is carbonate, and what you will get is an aldehyde, no alkyl group, isn't it? So, therefore, what aldehyde? Formaldehyde is coming. So, only calcium formate is taken, then out of 2 carbons, 1 carbon is lost as a calcium carbonate. So, formaldehyde comes. All acids are giving the ketones, but this is giving a aldehyde. Calcium formate will give formaldehyde. Mathematically 1 plus 1, 2 minus 1 means 1 carbon, carbonyl is obviously formaldehyde. You have another observation also. You take any carboxylic acid, calcium salt, plus this calcium formate also you add, formic acid, right? Formic acid, calcium salt, mix it. This is called mixture of the calcium salts of acids plus calcium formate. Then this corresponding acid aldehyde will come, RCHO will come. So, 2 RCHOs will be coming, and this will become into calcium formate, and then 1 carbon is added here. So, you will get a 2 moles of calcium carbonate formed, 1 calcium here, 1 calcium here, both will become into calcium carbonate, and both these carbons are becoming into the aldehyde. So, you have 3 observations. Any calcium salt of the acids beyond the formic acid, that is starting from acetic acid, propanoic acid, their corresponding ketones are formed. Calcium formate alone if you take, you will get formaldehyde. If calcium acetate of a carboxylic acid mixed with the 3 carbon acid, I have taken added calcium formate, 3 carbon aldehyde, no loss, no gain. So, number of carbons in the acid, as such you will get as an aldehyde. So, the method can be used for all different types of the aldehydes, all ketones, including specially formaldehyde also can be prepared. So, the method is applicable for all ketones and all ketone aldehydes, but you have to choose which method is exactly fit for the what type of compound you want. All this 1, 2, 3, 4, that is oxidation of 1 degree, 2 degree alcohols to give aldehyde ketones, hydration of different types of the either acetylene or containing or dialkylated alkynes can be hydrated to give the corresponding ketones, hydrolysis of gem dihalides. The gem dihalide can be 1,1 type or 1,2,2,2 type, but not 1,2 type. The halogen should be on the same carbon, either in the middle or in the terminal. You get aldehydes and ketones. So, in this method also you get aldehyde and ketones. So, all these 4 methods are used for the both aldehydes as well as ketones. But for this 4th method, we have slight complication. Let us take that as a separate issue. But all these 4 methods are very simple, applicable for the both aliphatic, aromatic, as well as aldehydes as well as ketones, both. So, we have some versatile, that is application is there for these 4 methods. As such, the methods also simple. So, let us put under this heading simple methods, right. So, let us take some special points regarding this pyrolysis reaction. As we have seen already, 3 points we have covered. One is any calcium salt of acid, when you pyrolyze it, corresponding ketones will come, right. Second point is when calcium formate alone if you take, you will get the formaldehyde. Third point is if you take calcium salt of any carboxylic acid plus calcium formate mixture when you do, you are getting the aldehyde. These 3 points already covered. But instead of the calcium salt. So calcium salt will have like this, isn't it? Attached to the calcium salt. Now the fourth point as an extension, let us take, if these two acids are attached like this, then this acid is not a common acid, it is a dicarboxylic acid with the calcium salt, right? A calcium salt having the two acid ends are there attached with the same backside. So compound is now called up to 2 carbon acid dioic acid is oxalic, malonic, succinic, glutaric, adipic. This is an adipic acid calcium salt. So let us call it as a calcium adipate. So calcium adipate on pyrolysis or heating strongly, what happens? We know that is calcium carbonate formation, then these two will be joined. Here already a joint is there, so the compound comes out as a, both are attached to the one carbon. So let us write in the center that carbon with a ketone, that is, it is a cyclopentanone, okay, cyclopentanone. So observe that this compound is a ketone, but it is a cyclic ketone is formed. So similarly, if I take a carboxylic acid having the 7 carbon calcium salt will result in the 6 carbon ketone. So what is happening is, one carbon is losing in the form of calcium carbonate. So therefore, if I take 7 carbon dioic acid, you will get 6 carbon ketone, 8 carbon dioate, you will get 7 carbon, 1 carbon less. But what about the other side? That is, if 1 carbon is less, this is already 6, you got 5. So if I take the 5 carbon acid means a glutaric acid, that is calcium glutarate. Calcium glutarate is supposed to eliminate calcium carbonate, and you are supposed to get the 4 carbon ketone. Unfortunately, these 4 carbon ketones are unstable, therefore you are not getting the 4 carbon ketone. The reaction is slightly deviated. So now what you will get is this 5 carbon acid dicarboxylic acid on pyrolysis, instead of giving the 4 carbon ketone, a 5 carbon anhydride is formed. 5 carbon anhydride means glutaric anhydride. Now we are interested not the name of this compound, but an anhydride is formed. Previous case ketones are formed. Do you have any method of that is verifying whether anhydride or ketone means? Add some water and see. In the anhydride case, immediately it becomes back into the acid, dicarboxylic acid. Anhydrades are unstable. So we have one statement in the anhydride. Anhydrades are anhydrades as long as there is no water available to it. If water is added, it will become into 2 carboxylic acid, that gives the glutaric acid back. So anhydrades exist as a anhydride. If you add water, it becomes into diacid. So whereas the ketones will not have any much reaction with the water. So therefore you can verify whether anhydride is formed or a ketone is formed. So this particular point enables you to identify certain thing here. So we have, in addition to this, I will explain one more fact. If I have a 6-membered ketone, okay, a 6-membered ketone can be converted by oxidizing into a 6 carbon oic acid. This is an oxidation. What oxidation means? If you do vigorous oxidation, sometimes the reaction may be violent, but the reagent you must select and under observation, that is, let us write it as a careful oxidation. Okay, a careful oxidation with nitric acid will cut this either this side or that side. So you will get a dicarboxylic acid, that is adipic acid can be prepared. Then you convert by adding the calcium hydroxide. You can go for the making into a calcium salt. Both the side you will get the anion and attached with the calcium salt. This on pyrolysis you are getting a 5-membered ketone. So we have a procedure now. How do you convert a 6-membered ketone into 5-membered ketone? Just 3 simple reactions. One is oxidize into dicarboxylic acid, make a calcium salt, and pyrolysis will get this one. So, a higher ketones can be converted into lower ketones by having these three. If these three steps, if I apply on this, you are not going to get 4 carbon ketone. Instead, you get an anhydride. So, this particular point, if you can apply, you have one method called, one scientist gave one. There is a method called estimation of size of the ring. Let us have a ketone with n number of carbons are there. We don't know how many carbons are there, but a number of carbons in this compound, let us call as n. This compound is applying these steps. What are that? First HNO3, right, that is oxidation. Then you have a calcium hydroxide, convert this dicarboxylic acid into the calcium salt, then apply the pyrolysis reaction. So, what you will get is, you get another ketone whose number of carbons are now the n-1 carbons are there. Here n number of carbons are there, which have become another ketone with n-1 carbons. Then again you apply the same 1, 2, 3 steps, okay, one after the one. Then what you will get is, you will get another ketone is formed, whose number of carbons will be one more carbon less. Let us call n-2 number of carbons are there in this ketone. On that, if I apply this 1, 2, 3 successfully one after the one, I got an anhydride. So, this anhydride is formed. Immediately you can guess, in this case the anhydride is not formed, means that is the closure point has come. Now, in this case you are getting the ketone, isn't it? But if this is applied successfully, you are getting anhydride. So, this ketone must have number of carbons will be 5 carbon ketone. The 5 carbon ketones only you will get anhydride, which is having a 5 carbon anhydride. The anhydride must be glutaric anhydride, and this ketone must be the, let us number it as a compound A, compound B, compound C, right. So, the compound C is nothing but the cyclic ketone, which is a pentanone. What is compound B means? It must be a 6-membered ring. What is compound A means? It must be a 7-membered ketone. It must be a 7-membered ketone. So, cycloheptanone. Now, the question is, I will frame like this: a compound on reaction with 1, 2, 3, compound A gave a B, and compound B repetitive again 1, 2, 3 steps furnished C, but the C on reaction with 1, 2, 3 gave an anhydride. What is the size of the compound A means? It is 7-membered ring. It is a ketone, obviously I am telling. But what is the number of carbons involved in the cycle of this compound A means? 7 carbons are there. 7 carbon is giving a 6 carbon reduction in 1 carbon. 6 is giving 5 carbon. 5 is supposed to give 4 carbon ketone, but 4 carbon ketones are unstable, therefore anhydride is formed. So, at this point you catch the point and then say that C is 5-membered ketone, B is 6-membered ketone, therefore A is 7-membered ketone. The method is given by a scientist called Blank. This is a Blank's method it is. In this method, we are able to estimate the ring size, just like estimation of reactive hydrogen Jervitnoff method, like that. This is a estimation of a ring size is given by a scientist called Blank, in which that 4 or 5 principles of pyrolysis of the acids if you have, on that basis this method is extended. So, now let us go for the second type of method. They are all something special methods. The special method means they either have some specific name of the reaction like Rosenman reduction and so on, or at least the method will be little complicated and specific in the method. All such methods let us put under this second methods. And these methods are now like that. The first method, let us go. A name reaction like Stephen's reduction. In this reduction, alkyl cyanides are treated with the stannous chloride and HCl in presence of water. The compound will become into an aldehyde. If only the two compounds are given, a cyanide to aldehyde, the question is given, a cyanide is converted to aldehyde, was it a oxidation or reduction? Means there is an oxygen insertion, therefore it must be an oxidation. But strictly speaking, cyanide is after the aldehyde chapter comes. That back chapter is converted to aldehyde, means it is a reduction. It is. So oxygen is coming, but the nitrogen we are foregoing, isn't it? Therefore it is a reduction. So many times HCl and tin and HCl is used, but here stannous chloride is used. In this reduction, stannous chloride converts into stannic chloride, SnCl4 is formed, and the nitrogen is converted to ammonium chloride. If hydrogens 5 are there, so if 3 HCl is taken, I think it is the balanced equation. So 1 mole of cyanide with 1 mole of stannous chloride with 3 moles of HCl and water becomes into the ammonium chloride, stannic chloride, that is 2 plus 3, 5. So it is, I think, balanced it is. So an aldehydes, so the method is not for the ketones. All cyanides are converted to aldehydes, only for aldehydes. So you can remember that there are some methods used only for aldehydes. This method you cannot use it for the ketones. Similarly, you have another method like a name reaction called Rosenmund reduction. Rosenmund reduction. The reduction involves an acid halide, like specifically chloride, acid chloride with hydrogen as a reagent, but the catalyst is very specific, that is a barium sulfate, palladium supported by the barium sulfate. In the barium sulfate, the sulfur is there, which is partly decatalyzing the palladium. If it is not there, it will give alcohol actually. But because of the sulfur presence and another organic solvent, quinoline, these two, quinoline and the sulfur present in the barium sulfate, are decatalyzing the palladium some extent. Therefore, the reduction takes place only partially, and it is becoming into an aldehyde. It is becoming into aldehyde. Actually, the reaction, if you see, I think the sigma bond we are breaking. No, actually the hydrogen is added on the here 1 carbon, here 1 hydrogen, here 1 hydrogen. So this OH and Cl cannot exist on the same carbon. So HCl will go out, immediately it becomes into aldehyde. It's a partial reduction. Specifically this catalyst, palladium supported barium sulfate quinoline, is given by a scientist called Lindlar. So the catalyst is called Lindlar's catalyst. The catalyst is also known to convert a selectively triple bond into the double bond. We have taken this point under the alkenes specific preparation from the alkynes. The same catalyst is also useful in this case. However, hydrogen and this catalyst together should not be said. Hydrogen acid chloride going to react in presence of Lindlar's catalyst. So the Lindlar's catalyst refers to only the combination of these three. Palladium, barium sulfate in presence of quinoline solvent is called Lindlar's catalyst. The catalyst has a selective and a partial reduction. Actually, the aldehyde can be further reduced to give the primary alcohol. But in this case, the reduction is we are able to stop at aldehyde level. So this is again a specific method. Similarly, we have another method called a Waker's process. Waker's process. In this process, an alkene like ethylene is oxidized with atmospheric oxygen in presence of palladium chloride and copper chloride, Cu2Cl2, cuprous chloride and water. All these three works as a catalyst, and this oxygen half a mole is consumed. That half a mole is adjusted alkene and you will get acetaldehyde. All these three are working as a catalyst. The reaction can be sub-classified into ethylene plus palladium chloride and water, and then water with copper chloride. All that three reactions you can write, but final reaction is this is what all three are now the catalysts only. The half a mole of oxygen oxidizing this one. However, in the case of the propene, we are able to get with acetone. So, the oxidation of alkenes with that is alkylated alkenes are giving ketones, but only ethylene is taken, you are able to get the acetaldehydes. Commercially very all these are regeneratable item. What you are consuming is only the oxygen, that too from the aerial oxidation, that is oxygen we are able to take from the atmospheric air. So, the reaction is a almost a spontaneous reaction to get this acetaldehyde. For industrial method, it is totally commercially very much the feasible reaction. Let us go under the specific that is special methods here. The fourth method, Neff reaction. Nitro compounds can react with sodium hydroxide. Because of the alpha hydrogens, they show tautomerization and exist as a acidic form. So, the acidic forms are readily react with sodium hydroxide. So, adding sodium hydroxide given nitro compound first convert into the nitro, that is sodium salt of nitro compound. This is called sodium salt of acid form of the nitro compound. This undergoes reaction with the concentrated sulfuric acid. Actually, this step, the oxidation of the sodium salt with sulfuric acid at 0 degrees centigrade, that means you are cooling the reaction. In fact, if you apply the temperature, the vigorous oxidation may be affected. So, you are cooling the reaction, the silent hydrolysis takes place and the corresponding aldehyde is formed here. A similar reaction with the nitrogen becomes into ammonium sulfate. It seems the main compound is aldehyde. If the compound is a 2-nitro, that is 2 degree nitro compound, if I take this hydrogen also can show the acid form. So, double bond N with O salt, Na salt, and with like this. This compound similar Neff reaction. This is actually Neff reaction. The Neff reaction is an oxidation of a sodium salt of acid form of the nitro compound 1 degree to aldehyde, or 2 degree compound with sodium salt with sulfuric acid becomes into a ketone. So, a ketone as well as aldehyde both can be prepared in this method. This is an aldehyde. Similarly, if a 2 degree compound if I take so 1 degree are giving the aldehydes and 2 degree are giving the ketones. It's an oxidation of a nitro compound into the carbonyl compound. Neff reaction. In the fifth method, it is also a name reaction called open air oxidation. In this oxidation, we have taken a compound A is an alcohol. This alcohol is converted into the compound B, let us call. So, A is oxidized to B, therefore, it is called oxidation. So, the compound A having the R1R2 is converted into R1R2 ketone. So, alcohol is oxidized. So, the desired ketone whatever you want, that corresponding R1R2 choose it and then oxidize it. It is here unfortunate, we are preparing a carbonyl compound B, but we are using a carbonyl compound C also. See, the carbonyl compound is a scapegoat, that is sacrificing carbonyl compound. One carbonyl compound is undergoes a reduction here. So, in this method A to B is an oxidation. This is called the open air oxidation. In fact, the B to A is a reduction. Any compound reverse reaction is a reduction, but that is not I am telling. While A is converting into the B, the compound B is converted to D, which is a reduction. So, another scientist, they have developed this method also. A suitable compound D can be prepared by taking the C also, that is a reduction. So, in this oxidation there is a reduction is also taking place. That reduction is if the compound C is a cheap compound, the cheaper compound undergoes reduction, but a costlier compound, a preferable compound B is prepared out of the A. So, A to B is a openoid oxidation. When openoid oxidation is taking place, there is one compound C that is undergoing a reduction. This reduction is developed by three scientists called Merwin Pondorf, Verily. These three scientists identified there is a reduction taking place, therefore, this is shortly called as MPV reduction. What is MPV reduction? It is a simultaneous reduction when compound A is undergoing openoid oxidation, compound C is undergoing MPV reduction. But in openoid oxidation, compound C should be a very cheap compound, so that the cost of this utilized ketone will be less. But our compound, that means here in fact the hydrogens removed from this particular hydrogen, removed minus of H2, this is going to add here, it is a plus of H2, that becoming into reduction. But what is the catalyst? A suitable catalyst is used here. This is an aluminium with a oxygen attached isopropyl group. So, the isopropyl alcohol aluminium salt, it is thrice will be there, aluminium valency is thrice, call it as a aluminium isopropoxide, thrice it is there. This 3 you need not to mention because aluminium is plus 3. So, therefore, 3 anions will be there, and that is isopropoxy groups are there. Aluminium isopropoxide is almost a unique reagent in the organic chemistry. Whenever aluminium isopropoxide comes, recall it must be an either openoid oxidation or MPV, that is Merwin Pondorf Verily reduction. In that case, this aluminium propoxide is used, right. So, in this reaction what we are using is compound A is oxidized to B, simultaneously compound C is reducing. The compound C should be, so we have given a compound C should be a acetone, compound should be acetone. In why it is acetone, we are giving the explanations. One is acetone cost is low. So, if I utilize this cost less compound, the reaction will become more, that is feasible or commercially more befitting reaction. I will get the bigger amounts of the profit. This is a cheap compound. So, I use this cheap compound, and the costlier the ketone B can be prepared. So, the acetone is a low cost one, small compound, so low cost. So, the cost of the acetone, why acetone, if somebody asks, the first reason is cost wise it is low cost. So, therefore, it is. Second one is its boiling point will be less. Why should I have low boiling point? Means you take more amount of the acetone, some acetone will be reduced to alcohol. After the reaction, the acetone and this isopropyl alcohol, because they are smaller compound, they will have a low boiling point. So, whenever the low boiling point is there, after the reaction working is easy, because they can be evaporated and they go into the atmospheric air. So, the separation of C and D from my compound, that A is already converted to B. So, with B some C and D will be there, this C and D can be removed by evaporation itself. The third point is acetone is a very good solvent. So, if you take more amount, it works as a solvent. So, acetone, if I take excess amount, it works as a solvent. Finally, what we have another application is the acetone directly will not become into this one, but acetone goes into this one, and then from this an alcohol is coming out. So, it is getting exchanged with the catalyst. So, if I take a butanone, after some time the aluminium isopropoxide will become into the aluminium butoxide. So, the aluminium butoxide will not have this specification. Therefore, acetone is a must. So, the fourth point is exchanges exchanges with catalyst. So with catalyst it is exchanging. So therefore finally I want to say the acetone must be the used here. Similarly, when I am doing MPV reduction, the compound A should be the isopropyl alcohol, which is converted into acetone, both can be removed. So my aim will be in the MPV reduction, compound C is reduced to alcohol. So this alcohol will be there. Our main aim at the target molecule is compound D will be our target molecule in the MPV reduction. In the openoid oxidation, target is B. B I am preparing by utilizing the compound C, that is a castless compound I am using, and the compound B is I am preparing. So MPV reduction and openoid oxidation are parallel reactions taking place in the same flask side by side, but which is costlier one? If you see the costlier one, if it is alcohol, it will become the openoid oxidation. If the costlier ketone is costlier one, then it will become a MPV reduction. So the angle of looking that reaction is different, but MPV and openoid oxidation both takes place simultaneously in a common flask. Right, this is what again a commercial reaction. So let us go for next special methods under the special method. Alkyl cyanides react with a Grignard reagent RMGX. Alkyl cyanides involve a triple bond. On this triple bond, RMGX shows a nucleophilic addition. R minus is added on the carbon, magnesium adds on the nitrogen. An intermediate substance like this 2 R's containing N minus MgX plus is formed. Now this is a salt formation. We have triple bond, so therefore we expect in fact twice RMGX may be added. That is, after adding one RMGX, one more double bond is there. There is a question in book, why not this RMGX, this salt undergoes one more addition? Already N developed a minus charge. If one more RMGX is added, N will become minus 2 it seems. So that's why one more RMGX will not be added. So this becomes as a salt. This salt if you hydrolyze with the H3O plus, the pi bond opens, twice the HOH, 2 OHs will become into a carbonyl group. So 2 R's, that is, if I take a R containing cyanide, you will get ketone, but it's also extendable to the aldehydes preparation. If you take HCN, add RMGX followed by the hydrolysis. Okay, so H with the R is added, so NMGX. This on hydrolysis you will get an aldehyde also you are able to prepare. So hydrogen cyanide with RMGX will give the aldehydes, and RCN and RCN. This R is 1 R coming from cyanide, 1 R from the RMGX. So 2 R's are coming, a ketone is formed. So the method is extendable for aldehydes as well as ketones. But though there is a triple bond, observe that only 1 RMGX is being added. The salt stuck up here, when you hydrolyze it in acidic medium, then it gives the ketone. So in the case of HCN, an aldehyde is formed. Similarly, alkyl, that is acid halides, react with RMGX. Now in this case twice reaction takes place. An R is added here, MgX is added, finally that MgX2 will go out, you will get first ketone is formed. So R, you too can say R replaces the X minus, simply you can say ketone. But the ketone now adds one more RMGX without any intervention. The R will be added, so you will get a 3 R containing alcohol, that is called what? A tertiary alcohol magnesium halide salt is formed. This salt, if you hydrolyze it, you are getting a tertiary alcohol. Now see the method. The method starts from the acid halide, gives a ketone, but this ketone is a very reactive intermediate product is ketone, but again reacts. The question may be, if asked 1:1 ratio, if you take, what happens? We may not control the reaction at this level, so therefore some product will go to the tertiary alcohol, some product will be recovered as acid chloride, but you don't get total as a ketone. So therefore getting the ketone in this method will become obviously an incorrect method. So, it leads to give the tertiary alcohol. So, our aim is to stop at the ketone, but we are not able to stop at the ketone. So, RMGX is more reactive, that is why double reaction takes place. You are getting a ketone, but once again participate, you will get the tertiary alcohol. In fact, we want to stop at the level of this one, but we are not able to stop. So, there is one method. Instead of RMGX taking, you treat RMGX with the cadmium chloride. So, 2 RMGX will react with this cadmium, forms into R2CD. This is called dialkyl cadmium, and magnesium will become into magnesium chloride. This dialkyl cadmium will have less reactivity. Now, you take the acid chloride, add this dialkyl cadmium. This the R will be replacing, and you are getting a ketone, and this ketone is not going to react with the further. So, you take 2 RCOCl and balance the reaction to give the cadmium again chloride. So, this is your product, a ketone. So, ketones can be prepared from the, in fact, RMGX only, because RMGX I have taken converted into R2CD, then added on the RCOCl. So, what is our main that is ingredient means I am using RMGX and RCOCl only, but directly if you add, you will get tertiary alcohol. Convert into a cadmium compound and then add it, you are getting the ketone. So, therefore, the highly reactive RMGX is converted to a less reactive cadmium compound, then add it on the acid chloride, you are able to generate the ketone. This is also under the specific method, you can take it as under the special method. So, under the special methods, you too can have one more method called hydroboration of alkynes. The method hydroboration means adding hydrogen and the boron, followed by the oxidation with hydrogen peroxide H2O2. So, let us take some R containing alkyne. So, unsymmetrical alkyne we have selected, add B2H6. H is the minus party, adds where hydrogens more. So, therefore, you will get RCH double bond CH with a R. So, the valency of the R is thrice. So, this is boron. So, to the boron 3 alkyl groups are added. So, call it as a, if it is saturated, you can call trialkyl borane, but this is alk. So, call it as a trialkyl borane. This borane, in fact, if I add any water, the OH goes here, H comes here, alkenes will come. But let us not add water or water type, that is proton containing solvents like alcohol, acid, you should not add. You add hydrogen peroxide, so that each side one OH goes this side, OH goes this side. So, thrice 3 hydrogen peroxides will be consumed, 3 alkenes will take 3 OHs, all 3 OH goes to the boron. So, boron will become into the trihydroxide or H3BO3 you can write. But this side what you will get is an alkene containing a OH, which is a anti-Markovnikov rule product. In fact, the rule we implemented is H minus added to the carbon. In fact, BH bond without breaking adds. But if you take it grant it is a hydrogen, boron is electron deficient, H minus adds, then we are following Markovnikov rule only in fact. Strictly in accordance with the Markovnikov rule we have added, but the product when oxidized with hydrogen peroxide develops into anti-Markovnikov rule, that is OH is added that side and it is tautomerizes to give the enaldehyde. So, generally if I hydrate it directly using the water in presence of acidic medium, that is sulfuric acid and mercuric ions, the hydration will give the alkene, that is ketones. this type of ketone, Barconi Kafrul products will come. But if I add hydroboration followed by the hydrolysis, the ene all goes that side, therefore aldehydes are coming. So, this is also one unusual method, in definitely it is a one special method. The lastly, we have a ozonolysis method. In the ozonolysis, already in the alkenes and alkynes we have thoroughly studied, but still a method like this, for example, an alkene select in such a way, one side one alkyl is there, the other side two alkyls are there. When you oxidize with first with ozone, so ozone is added and then rearranges to give the real ozone, ozonide is formed. The ozonide, if you hydrolyze in presence of zinc using, if you don't use zinc, that side okay ketone, but this side aldehyde further oxidizes to give the acid. So, reductive ozonolysis of this compound, one side generates a aldehyde, simultaneously the other side piece will be the ketone. So, you have a really a wonderful method. So far the methods are giving aldehydes and the ketones separately. The method is extendable ketone also I was telling, but here a suitable alkene if you select, half of the compound converts into aldehyde, the other half is converting into ketone. That is the speciality of this ozonolysis reaction. So, from 2-methyl 2-butene if I select, you will get acetaldehyde as well as acetone. Both simultaneously are generated. This is definitely one of the special method.